cell, the Redox Vodcast. We were just getting to cell EMF when we ended last time, the electromotive force. Lots of acronyms coming at you, so keep track. EMF, electromotive force, that is measured for each electrode when it's compared, any particular electrode, copper, zinc, is compared to a hydrogen electrode. That's considered the standard, and it is considered to have a 0-volt reduction potential. So everything is compared to that. And again, those reduction potentials are used to figure out the E of the cell by taking E of the reduction at the cathode minus E of the reduction at the anode. Okay, here's a quick picture of a hydrogen electrode. You use a platinum wire, which is not going to react with the acid or the hydrogen gas. And at the platinum electrode, the electron is carried through the wire and combines with the hydronium ion, or a hydrogen from the hydronium ion, making hydrogen gas. And if that is the reduction, then the other electrode must be going through oxidation. If the other one has a higher reduction potential, then this will go through oxidation. We use the half reaction hydrogen ion plus 2 electrons yields hydrogen gas, and we call that the zero, the She. Okay, here's the She set up with another electrode, in this case the zinc. So the zinc, as usual, gives away its electrons, being oxidized. I always have to think through that. And its EMF is 0.76 as compared to hydrogen. So the standard oxidation reduction potential of zinc is 0.76, is negative 0.76 actually, because it's compared to the hydrogen at 0. Because the zinc is going through the oxidation and the hydrogen is going through the reduction. So here are the two half reactions. Okay, so if we consider that zinc losing electrons, becoming oxidized, you measure the E cell relative to the standard hydrogen cathode, and the standard reduction potentials are written as a reduction reaction. So because the zinc is actually being oxidized, its reduction potential is written as a negative. When it was measured as an oxidation, it was a positive 0.76. As a reduction, it's negative 0.76. Here's the whole table. And hydrogen's somewhere here in the middle. Everything above hydrogen is more likely to be reduced because it's a reduction potential table. And everything below hydrogen is more likely to be oxidized compared to hydrogen. And that's true for any two electrodes on the table. They're always written as reductions, so you just remember to use them as reductions or think of them as going the opposite direction if they're being oxidized. We'll get some practice with this in class. Okay, so let's check. Would the zinc 2 ion reduce in the presence of the standard hydrogen electrode? Nope. Would the zinc oxidize in the presence of the standard hydrogen electrode? Yes. It's lower on the table, therefore it is less likely to be reduced and more likely to be oxidized as compared to something above it, such as hydrogen. The standard reduction potential is an intensive property. Do you remember what that means? Like it's internal, doesn't matter how much you have, how much zinc you have, it's always got that same reduction potential. Changing the stoichiometric coefficient doesn't affect the E of the cell, the standard reduction potential of the zinc. So even if you had to double it for stoichiometry, you'd still have a reduction potential of negative 0.76. It's kind of slick. Reactions with a reduction potential of greater than 0 are spontaneous compared to hydrogen, whereas ones like zinc that are less than 0 would be non-spontaneous. Reactions with the reduction less than 0 are spontaneous oxidations relative to the standard hydrogen electrode. The larger the difference, the greater the E of the cell, the higher the waterfall, so to speak. The more positive the value of the reduction potential, the greater the driving force for the reduction. Okay, here's a little video to tell you about standard reduction potentials.
The cell potential of a voltaic cell, such as this zinc hydrogen cell, can be thought of as the sum of two half-cell potentials. Under standard conditions, the cell potential, E0, is the standard reduction potential of the cathode, minus the standard reduction potential of the anode. We can assign half-cell potentials once we settle on a reference half-cell potential. That has been chosen as the hydrogen half-cell, with 1 molar aqueous hydrogen ion, and 1 atmosphere pressure of hydrogen gas. For the zinc hydrogen cell, the measured standard potential is 0.76 volts, and the standard half-cell potential for the cathodic half-cell is defined as 0. Thus, the standard half-cell potential for the anodic half-cell is minus 0.76 volts. This is the standard reduction potential for the reduction of zinc plus 2 ion. Now let's consider the silver hydrogen cell. In this case, the hydrogen half-cell is the anode. As before, the cell potential is the reduction potential for the cathode minus the reduction potential for the anode. Thus, the standard reduction potential for the silver-silver ion half-cell is 0.80 volts. Proceeding in this way, it is possible to measure and tabulate standard half-cell reduction potentials, such as these selected values. Remember that the standard half-cell potentials are always defined for the half-cell reaction written as a reduction. If the half-cell reaction is reversed, the sign of the standard potential is reversed.
Sweet. Nice little summary. Okay. So once again, that was Ursa. Hi, Ursa. The strongest oxidizing agent is at the top of the chart because it is more likely to be reduced. So it's causing oxidation. And at the bottom, they are most likely to be oxidized because they're the least likely to be reduced. They're the strongest reducing agent. That can get really confusing. So just always remember what oxidation is and what reduction is, and make sure it's clear each time you determine what's the anode and what's the cathode. Okay, so let's think about spontaneity a little bit. We'll get back to our delta G. We haven't talked about that in a while. For any electrochemical process, the E cell is cathode minus the anode of the reduction potentials, and if you have a positive E, that's spontaneous. If you have a negative E, that is non-spontaneous. Tricky how they do that. The delta G's have the opposite sign, don't they? All right, so that is used to understand the activity series of metals. So if we think about nickel with silver, nickel reacts spontaneously with silver ion to produce nickel ion and solid silver. The standard potential is the reduction potential of the silver, which is being reduced, and minus the standard reduction potential of the cathode, which is the nickel being oxidized. So it's 0.80 minus negative 0.28, which gives you a positive 1.08. Remember, if it's going to be spontaneous, the E of the cell is going to be positive. So if you get a negative number, but you know it's spontaneous, you know you did it backwards. All right, so electromotive force, and free energy. So this is the other way we think about spontaneity. For delta G, it's going to equal the negative, that's making that positive E into a negative number, times N and times F. What are N and F? Well, N is our old friend, the mole. And F is named after a man named Faraday. Did a lot of good work with electricity. And his constant is 96,500 coulombs per mole of electron, which is equivalent to 96,500 joules per volt mole. Cool stuff, huh? So delta G is the change in free energy. Delta G is negative, as I said, and when it's spontaneous. But delta E is positive. I'll get rid of those things. N is the number of moles of electrons transferred, and Faraday's constant tells you how many coulombs for every mole of electrons. And E is the EMF of the cell. Since N and F are positive, then delta G is negative if E is greater than 0, it's positive. So they're opposite when they are both referring to a spontaneous reaction later. Okay, that is all for tonight, folks.